Recording is on.
Awesome. Okay. Hi, everybody. So, as I said, I'm going to explain these three problems today. Tree BFS, breadth first search, and tree DFS, depth first search. So, there are slightly two different problems: depth first traversal and also searching. So what is traversal and what is searching? So you already know traversal is basically, as we discussed before, in order, pre-order, post-order. Those are the three popular traversal, like visiting all the nodes of the tree. Using BFS also, there is another types of traversal, and DFS is another type of traversal. So we will discuss those, and also we will also discuss about the searching, breadth first search and depth first search. So now go back to the um, thinking slate here. So let's say A, B, C, D, sorry, D, E, F, E, H, something like this. Okay. Now, can anyone tell what is BFS? If you know about BFS, and B, like breadth first BFT, I would say breadth first traversal. I don't want to call BFS. I'm not searching basically. So breadth first traversal. Yeah, go ahead. Go ahead,
Yeah,
Karen.
traversing at each level.
Exactly, traversing at each level. So what would be the output for this breadth first traversal? Anybody can tell us? Yeah, what will be the output for this one? So we'll go through the first level and then we'll go to the second level and then third level, right? So breadth first search. So A,
B
B, D,
B
uh-huh,
D E
uh,
C F G H.
exactly. So it's kind of breadth first search. So we'll cover the breadth. This is called breadth of a tree, right? So we'll cover the whole breadth of a tree and then we'll come back to the next level. So I think we did similar thing in maybe in one of the, I think last time you explained something, right, Karanya, like a linked list of things, I guess. So but anyway, so this is kind of covering each level. So root level, and then we always know that the axis is with root, so we always have the pointer to the root. So the we will start at root and cover that, and then we'll cover all the nodes of the next level and then all the nodes of the third level. So now let's go back and discuss about the DFS. What is the DFS? What is the depth first search? So let's select something else. Depth first. Depth first. So anybody can tell us the answer for this? Anyone? Karanya?
completing the right node of the, sorry, first completing the left node of the tree, subtree, and then going to the right
Uh,
node of the tree. Completing
going to
each,
the right.
yeah, from the root, completing the whole left subtree, and then
Mm-hmm.
traverse the again to the root, and from the root, completing the whole right subtree.
Okay. Yeah. So similar to that. That exactly. So basically, what we do is depth first. Depth means like if you are digging something, it will go down, right? So you start from a node and you go all the way to the depth of it. So as Karunya said, we usually start with left node. So for any tree, we will try to start with the leftmost node. So we start with A and then B, and then before going to the other nodes of A, we will go down, like we will see what is the depth of B, and then we'll go down to the C, and then we visited the C, and then we will see if we have any other nodes down C. So it's we will go all the way to the down, and then we'll come back. So once that there is no nodes, right, after C is like the last one, and then what we will do is we'll come back. So we'll come back to C is completed. Let's go back to the B again and see. Let do we have any other nodes like right nodes, or this is a normal tree. This is not a binary search tree, right? See that there are three nodes for A. So we will see if we have any other nodes, any other children for B. There is no children for B. and then we'll go back to the A. We completed one depth. We completed going all the way down with one children. We'll do the same thing. So now there is one more children for A, which is D. We will cover the D, and then we will see what is the depth of the D. So we have one more. After D, there is a F, and we will see do we have any other nodes under F. So we'll go down until we find the leaf node. So we did not find anything. F is the leaf node. Then we'll come back to the D and we'll see what are the other nodes. So now can you tell us anyone, Shashank, not yeah, Shivang, can you tell me the answer for depth first traversal of this tree? Did you understand
First
this
is,
logic?
yeah, I got it. First we have to do A, B, C, then we have to go to D, then F, then G, and then
A,
E,
B,
then
C,
H, then
D,
D,
F,
F,
uh-huh,
G, G,
D, F, G,
G, E, and H.
and we'll go back to the A,
Yeah, and
E, and H. Yeah,
H. Yeah.
exactly. So basically, that's the depth first search. Yeah, depth first traversal. So is it clear to everybody the
Yeah.
difference between the BFS and DFS? And it's not, of course, not searching, but depth first traversal and breadth first traversal. Modit and Cecilia.
Yep, makes sense.
Yeah,
Awesome.
like in
Yeah.
like in depth first search. So like
Yeah.
we are going to like root again and then look for the next node.
Exactly, because we haven't covered the other children, right? Let's say A
Yeah.
covered with A and then B to the C. We don't know what are the childrens of B. We haven't printed those. We haven't printed the other children of A as well. So we need to go back to the root node and find out do we have any other children which we did not cover, right? So
Yeah.
that's the thing. So
Yeah,
yeah,
got it.
even
Yeah.
yeah. So basically we need to make sure we did not miss any of the children. We should not miss any of the children, right? So we'll go to the depth and then we'll come back here. So this is different kind of, it's not, see carefully, if you look at carefully, it's not the any of these traversal not equal to the in order, pre-order, post-order. Those are completely different, right? So anybody needs explanation about the in order, pre-order, post-orders, or is everybody clear on those? Shashank, did you get a chance to look at those before?
Yeah, I know
Shivang, sorry.
what is in order. Yeah, it's fine. I know what is in order,
Yeah.
pre-order,
So
and post-order.
yeah. So last time we discussed it. I can share the algorithms if you want, but I can also share. I think we recorded the video as well. So now these two are completely different traversals, right? So now let's discuss how to print those. So there are two things, right? First one is printing. I want this answer. I will give this tree, and if I say BFS, best first first traversal, I want this answer. If I say DF, depth first, I want this answer. I want this to be printed, right? So now how can we do this? Any idea? Let's start with BFS, breadth first traversal. So now we want to do at the level by level. So please share your ideas. How can we do this? What data structure will help us to do this? And you always start at root. So what are you going to do? Any ideas? We covered a lot of data structures before. We started with the arrays, strings. We know about stacks and queues. We know about linked lists. So far, we covered a lot of major data structures. So let's see which one is best suited for breadth first traversal. Any idea? Just feel
I
free,
guess
just whatever.
array will work. I guess. I'm sorry. I
Okay, that's
said
good. That's good.
array.
So,
Yeah,
mhm.
I said
So
array
how the
will work.
arrays? Yeah, how the
We
arrays will work?
can.
Let's say, yeah, go ahead.
It's fine. It's fine. It's fine.
Yeah, go ahead. Go ahead. Please share. Yeah, here is the array. What are you going to do with the array? You start with A, right?
Yeah,
Mm-hmm. Yeah.
and
Please
and
explain your thought process. Yeah.
and then we just keep storing the values from left side. We will cover up the one level And
So
then
A
we
will be
just,
printed, and you
yeah,
want to put we want to put B and D in the array,
I don't know
right?
properly. Better you.
Yeah, no problem. That's a good. Just explain the thought process. So that's one of the good ideas, right? So you covered B and D, and then you print the B, and do you want to put C into the array?
I
Right?
don't know, sir. Yeah.
Yeah. But you started it with a good process actually, because you able to see my screen. Everybody able to see my slate, right? I just want to make sure.
Yes.
Yeah.
Okay. Yeah. So this is a good thought process because array will solve it, but let's see what are the problems. We can go with the same approach. Let's say A visited, and we can put B and D in the array, and then B visited, we printed B, and we put the childrens of this B into the array, and then now if you take out from the if you take out from the array D will be printed, which is good. Now what are the childrens of the D? F and G, right? um, yeah, now C will be printed. Am I doing wrong? Yeah, sorry, E is also there. So B D, so B D E, I forgot to put E here. But anyway, this process will work. But what are the problems seeing here? We are taking an element, we are taking out an element, and also we are inserting at certain points, right? So initially, let me put this again. So array solves the problem, but there are few issues with the array. So let's start with the problems of the array. So what Shivanki is saying is, we can put here a first element into the array, and then there is no other elements at this level, which is good. Now we will read the a and print it. We printed a. Now what are the childrens of the a? B, D, E, right? We'll put B, D, E into the array, which is good. Now there are no more children for a. Now we'll come back to the array saying, hey, remove the next element B. We'll print the B printed. After that, we will see what are the childrens of the B, which is C. We'll put C and then equation. So now let us look at the problem with the array. One is removing an element. There is no concept of removing an element, because only thing is you need to put a null value here, or you need to have a pointer saying these two are completed. Next time you want to read at the position here, let's say 0 1 2 3 4, right? So you need to maintain a pointer saying don't read 0 1 because we completed printing. Next time if you are asking an element, I will give you this one 0 1 2. So we need to either maintain a pointer, because we cannot remove the elements from the array. That is one problem. And also, let's see, is there someone joining, or I got some sound? I don't know.
Sorry. It was
No
mine.
problem. No problem. Yeah. So now after visiting B, we inserted C, right? In order to insert C, we need to find where to insert, because we can also take array with 100 elements. Okay. Let's say, oh, someone is calling me actually in the, wait, in the Discord. Just a minute. Huh? Hello. I'm getting a call in the Discord. Someone calling here. Hello. Oh, you called in the Discord. Okay, sorry. I disconnected. Okay. Okay, cool. Okay, so now the problem here is, see, when you are inserting C, right? You need to find location. You should not insert at the 2 or 3 because those are occupied, and you need to find next available location in the array. So you need to maintain another pointer, where you need to insert. So these are the complexities of this array, because you cannot remove the element, and also we need a lot of pointers to maintain where you need to insert the next element. Array is really big. You can take 100 elements. That is another problem. You don't know how many elements. When you are initializing array, you need to specify the size. Here you don't know the size of the tree, right? You initially when you start the program, you just had a pointer to the root. That's it. You don't know how much size of the array you need to take. If the tree has 200 elements, if you are taking only array of 100 element, your algorithm will not work, right? So it may work, but it may not be work, because let's say in the single depth itself, if you have 150 elements, A, B, C, and if you go all the way down, just in one left side you have 150 elements. You took only 100 elements of the array, the size of 100, your algorithm will fail, right? So this is the kind of thing. So maybe, or I'm saying wrong. So let's say in the second level itself, if you have 150 elements, in the second level itself 150 elements, you need to store all those elements B, D, E, and so on, right? So these are the problems. So array we cannot declare, and we don't know how many elements, and also we need to maintain the pointers. So now I think you understand the problem if you are using arrays. So now anybody can tell what is the best data structure to use in this situation. Breadth first, traversal.
So like we do not know the size, like total number of nodes basically, है ना? Sorry.
Exactly. Yeah, that's
So
good. Yeah.
So we will use a dynamic array, like array list.
We can do that, but again, arrays and array list has the similar problems. Like you don't have the facility to remove the elements, and also you don't know exactly where you need to insert. You need to maintain these pointers all the times. So we can achieve the similar functionality with another data structure, which is very easy. So we no need to have all these problems. So just think a little bit more. So something like this. There is a data structure where, see, if you look at here, you are inserting elements here and you are removing elements here. What data structure will provide that facility for you?
Queues.
Exactly. That's what I want. See, queue, exactly, simple. Queue will solve it. You're inserting elements at one end and you're removing elements from the other end. That's what it is, right? So I think it's queue is, I always forget. First in, first out. Correct? FIFO. Whatever you put in here, that will be the first one will come out. So you are putting the elements in the queue and you remove the elements and process it. So when you are removing, the queue data structure will take care of the removal of that element. Everything will be taken care. And when you are enqueuing, if you simply say enqueue, it will automatically enqueue at the end of the array. You no need to say, hey, put at the location number 4, put at the location number 5. You don't need to specify any index. But in arrays, you need to specify. So array of 5 equal to C or array of 4 equal to C. Otherwise, where it will insert, you need to specify the index. But in case of queue, you don't need to do anything. Just enqueue, dequeue, enqueue, dequeue. Correct?
Yeah. Yeah.
That's the advantage, right? So is it clear to everybody?
Yes.
Awesome. So it's just
Yeah.
it's simple, level by level. So level by level is queue. So it's simple here. Let's come back to the problem again here. I just closed it. So I'm going to before. So since everybody clear about the process, I will show the code. So let's say this is our tree. Okay, 1, 2, 3, 4. Let me put here. Okay, now here is the tree. Okay, I'm going to draw the tree here. So we have something like this: 1, 2, 3, 4, and 2 has 5, 3 has 6, 7, 8, and 4 has 9, and 6 has 12, and 8 has 11, and 10. See, this the order is different, 11 and 10. It's not 10, 11. So now So what will be the breadth first search? So what simple, like we already know breadth first search is right. So now what I'm going to do is let's process this using a queue. Okay, so we'll put a queue here. Let's say this is the queue. So queue has the elements will be inserted at the last, and from the front the elements will be exited, right? So now what we say is we will go to the each level and we'll put all the elements in a queue. Breadth first, right? So we'll put one here, and then we are done with the level. First level we are done. So once you are done with this, now we will enqueue the queue. So we'll enqueue the queue and we'll print the one. Not enqueue, sorry, dequeue. If you are dequeuing, we'll print the one here. Let's say I will put somewhere here. So now we are done with one. So now what we need to do is we need to put all the elements of the second level into the queue, right? 2, 3, 4. Now we are done with the second level. There is no more children, right? Now let's process the queue. So as long as the queue is there, let's say we processed the queue, processing in the sense dequeue. We dequeued the element and we printed 2. Now before processing next element, before processing the 3, we will see if we have any children of the 2. If we have any children of the 2, let's put those elements into the queue, because we have to process at some point, right? So since once you remove the element, you put all the children into the queue. So 2's children is 5. We'll put it in the queue and we are done with queue. So we are done with 1, we are done with 2. Now what is the next element in the queue? The next element is 3. We'll print 3. And what are the elements, what are the children of the 3? We'll put all the children of the 3 into the queue. 6, 7, 8, right? The queue will increase like this. So queue, it's dynamic, right? Queue is always dynamic. So we no need to mention how many elements, it will dynamically, it will allocate the memory, right? So now 3 is completed. We printed 3 and 3's children also added to the queue. 5, 6, 7, 8. And then 4, we process the 4 and 4 children added to the queue. Now see that we are completed 2, 3, 4. We completed that level. Now process 5. There are no more children for 5. Now process 6, and the 6 children will be added to the queue. It will go like this, right? So now we are in a good shape, right? We are printing level by level, 1, 2, 3, 4, and then 5, 6, 7, 8, and 12, and then 10, 11, and 10. It will print like that. 7, 8, 9, of course 9 will be printed, and then 12, 11, 10. So is it clear to everybody? Right?
Yeah.
Yes.
Yeah. Now let's before showing the algorithm, it's very simple. I just whatever I explain, I will show the same thing. Now let's talk about the breadth first search as well. BFS. We just discussed about breadth first traversal. Now let's discuss breadth first search. It's just nothing but searching for an element using breadth first traversal. Basically, let's say, hey, I will give you the pointer to the tree and I will ask you, do we have 7 or not? I will give you the element. So find 7. Do we have 7 in the tree?
Yes.
Do we have 7 in the tree? Yeah.
Yeah.
Right? Yeah. So because we can say yes, because with our eyes we can see 7 is there in the middle here. But if I gave you the, if you are using algorithm, you need to algorithm need to execute from the root, right? Algorithm either need to use any of the traversal, in order, pre-order, post-order, or BFS, DFS. You need to traversal, you need to look for the element, right? So this is one way of looking for an element. So you can use in order, you can still use post-order, I think, and all those, basic algorithms you can use it, but every algorithm has its own problem. So breadth first search is another, way of finding an element. So what you do is same thing. You will traversal, you traversal the first level. Now what you do is you look for the element 7. Do we have 7 in this level? No. Now you traversal all the elements here. Do we have 7 here? No. Next, you traversal the next level. Yes, you found 7 and you stop there. You don't need to traverse the other elements, right? But in case of traversal, we are not searching for anything. You are printing every element. You print all the elements until last element. But in case of finding, once you find the element, you're done. You don't need to traverse the other elements, right? So this is one way. This is a breadth first searching for an element. So no sorting here. I just put the 1 2 3 4 in the sort. There is no, not necessary, there is no requirement or the condition that the elements are sorted. Even the elements can be alphabets or objects, as I showed in the previous example, A B C D. So we don't know the order. It's not binary search tree. Binary search tree has an order, right? I think we discussed in a couple of weeks ago. So binary search tree has an order, like the value of the left is smaller than the value of the root, and the value of the right is greater than the root. So there is an order. So in the binary search tree, and also only 2 children. So that gives you the flexibility to find faster, because there is an order. Elements are in a particular order. Every element satisfies some condition, right? But here it's a normal tree. It's not a binary search tree, and there is no order. There is no the element 7 could be here, 7 could be here. We don't know. 7 could be anywhere in the tree. So only thing is you have to use either BFS or DFS. So if you given a tree, just a normal tree or normal binary tree, not binary search tree. If I gave you the two things, normal tree, many nodes, more than 2, right? Here we have 3 nodes. Here also we have 3 nodes. If I'm giving you the normal tree, or if I'm giving you the normal binary tree, which does not maintain that order of the binary search tree, then there are only these kind of 2 basic algorithms to find an element: breadth first search or depth first search. Okay, are you guys clear?
Yes.
Yes.
Let's look at the code. It's exactly what I explained, nothing different. So I'm going to show the code now. So bear with me. I don't know how, if I can increase the font. Is it visible? Or so I think the shortcut to increase the font. What is that in the code, Visual Studio Code? Zoom.
It's visible, sir.
Zoom. It's visible. Okay. Yeah. So basically, created these nodes. So how I created is, I just created I created a class called node. Node has data, which is integer data, and children. Look at this. It's not left or right. In the normal binary tree or binary search tree, I will create left and right. But here, I don't know how many children at each level. A node can contain n number of children. So I created a list. A list could be this is in C#. I use C#, but in Java, everywhere we have similar things. So it's a dynamic list children, and you can add any number of children, and get children will give you all the children. So get children will give you whatever the children of this element. Let's say for the element 1, if I say get children, I will get 2 3 4 at a single click. Just if I call this get children nodes, child nodes, get child will give you all the children of this particular element. Okay, so this is a public method, and node is basically a constructor. When you are initializing a node, you need to say what is the value of the node. Okay, so this is the basic class I created. Now I created all the nodes. I created node 2 3 4 2 3 4 yeah, at the second level, and 5 6 7 8 9 at the third level, and 10 11 12 at the last level. 10 11 12, of course I created in a same order, 10 11 12, but when I'm adding, I added a different order. See, this is the way to do it. So n1 dot children dot add 2 3 4 So I'm creating one with all the nodes. N1, where is N? Yeah, N1 is already here, right? So I'm adding the node 1, node 2, 3, 4 to the N1, and node 5 to the N2. Just creating, basically this is all talks about creating of the nodes, creating of the basic tree, which we no need to do in any interview, but I'm doing it because in order to execute the program, I need to have a tree, right? So if you look at here, for 8, I added 11 and then I added 10. So that's why it is like 11 and 10 for 8. So 8 children are 11 and then 10. So, and 6 children is 12 here. So, and 6 dot childs dot add. So now let's go back here, breadth first traversal. So here is the breadth first traversal. As I said, we are giving only the pointer to the root N1. N1 is the root node. That's it. And now run BFS. So this method will say, hey, run BFS. Here is the root node. Find, do we have 8 or not? Run BFS. Here is the root node. Find if we have 15 or not. Do we have 15 here? We don't have 15, right? So it will say either find the element or no, we did not find it, that kind of answer. So this is a running program. So let's talk about let's look at the traversal.
So
So very simple. Yeah,
excuse me. Yeah.
go ahead. Go ahead.
This statement you said, run BFS N18. So basically, it will look
Yeah.
in the children of N1 only, right? Or the whole tree.
No, it's a whole tree. Basically, when all the tree problems, we will give only the root node. So
Okay, got it.
even in the linked list, right? It
Yeah.
starts with root node, but it will navigate all the childrens of the tree, not only just
So,
N1.
what's
Okay.
the endpoint? What's the loop out condition in the tree? Like,
Yeah.
if you're
So
traversing it,
as I said here, yeah. Go ahead. What is your question? Yeah.
question is like if we are doing some traversing, so we need to get
Yeah.
out we'll use loop or something, right?
Yeah.
Yeah. So my question is, what is the ending condition for that particular loop? Like,
That's a good idea. So ending condition here is, let's say you are looking at the tree, right? I will say, do we have 15 in the tree?
no, no.
How did you find it? How do you say that there is no 15? What you did in this few 3 seconds or 2 seconds, what you did?
I just look at the tray
You look
visually. Yeah,
exactly visually you looked at all the notes here, right?
yeah,
And you answered when you say you did not find 15 because you already seen all the notes here,
yeah.
and you did not find 15 and you say no. That's what we do. That's the ending condition. Once you visited all the nodes, if you are finding it, good, that's ending condition. Let's say, did you find 8? Yes,
Yeah.
because you see here 8 is there. So once you find 8, you stop looking at the other elements 12, 11, the 12, 11, 10, because you already found 8. So you no need to traversal down the tree. Let's say if I give you the tree of 50 elements, you no need to go down because you already looked at 8 is there, right? So that's the ending condition. Either then there are two ending conditions. One is either you found the element, stop there, or you complete all the elements of the tree.
Okay, got it.
So that's a very good question, actually. Whenever we are looping, whenever we are searching, whenever we are traversing, definitely there should be an ending condition. So I forgot to say that before. Thank you for that. So here, even in the breadth first traversal, when you are traversing all the elements, what is the ending condition? Ending condition is as long as the queue is not empty, we need to process all the elements. Once the queue becomes empty, that means there are no more children that we need to process. That's the ending condition for breadth first traversal. So breadth first search also similar thing, until we don't find any elements in the queue, or we find the element what we are looking. So for searching, there are two ending conditions. For traversal, only one ending condition. Like for traversal means you're not looking for any element. You need to process every element in the tree. That means until the queue is empty, right? So that's a good question. So that's what we are going to do here. So now let's look at the traversal. Traversal, here is the root, and you know, root, if root is null, this is the base condition, right? This is a kind of a checking condition. If the root is null, if someone says like, breadth first traversal of null, so there is no tree doesn't exist, so you don't need to do anything, just return, right? If there is some nodes, that means you need to create a queue, as I said before. So for traversal, what we are doing is we are creating a queue, and as I said, we are adding the first element into the queue, q.enqueue. So I don't know, I want to increase the font. Anybody knows, tell me how to increase the font. I think it should be under edit, right? Edit. No, it's not edit. View, probably it's a view, appearance, layout, layout, appearance. Yeah, zoom here, I think. Zoom. Do we have? Yeah, zoom in. This is the thing. Yeah, is it clear now?
Yeah.
Is it more visible? Yeah. So what are we doing here? We are putting first element, the root element, which is 1. We are putting 1 into the queue, and then we are taking a node. So this is just a pointer kind of thing. We want to process every element from the queue, right? So we took a variable called node, and then here is a while loop. See the ending condition here. If the q dot count not equal to 0, this is the ending condition. As long as the count will give you, returns the number of elements in the sequence, in the queue, number of elements in the input sequence. It says input sequence means basically the queue here. So as long
Sir,
as,
can you explain this better again? I'm sorry to
yeah,
disturb you.
sure, no
Thank
problem,
you.
and stop me anytime. So what we are doing is we are executing these lines as long as we have a queue of count not equal to 0. If the q dot count, what is the q dot count initially? At this point, let's say we started at root 1, we started at the root, which is 1, and we added 1 here, the node 1 here. And what is the count at this point? 1, right? Because you just added 1 into the queue. You just added the node 1 into the queue here, right? In an empty
So
queue.
where are we adding the one? Like in which sentence? Can you just can
That
you
is
show me the
called
code?
this one, NQ.
NQ. Okay, I got it. Yeah.
At the line number 91, we are adding that root element into the queue, right?
Yeah.
So when you come to the line number 93, what will be the count? Count is 1. 1 is not equal to 0. That means you have one element to process in the queue, right? So now what are we doing? We are starting processing the element. So node is just a variable. Node equal to q.dq. What will happen? At this point, the 1 will be removed from the queue and 1 will be assigned to this variable. Now we are printing the 1 dot data, like node dot data, which is like the value, the value, the 1 will be printed on the console. Now, as I said before, what we need to do is we need to get the children. Actually, childs, you can also say node dot get childs, right? Get child nodes. Yeah, get child nodes. If I say get child nodes, this will give you all the children of the particular node, whatever you dequeued. At this point, we dequeued the 1, and this method, as I showed before, here get children will give you all the children of the 1, right? So how many children of the 1? There are 3 children of for 1, right? So we are, for each kind of, it just for each is a loop in C#. So I think in Java also we have for each. I don't know if you guys are using different languages. This is just a for loop. So for each node of this children, we are putting into the queue, q.enqueue. So basically this for loop will make sure all the children of 1 will be inserted. So if I go back here and say, as I said before entering into the while loop, this is the situation, right? We put the one in, we placed one into the queue, and once you enter into the while loop, we removed one, but we need to enqueue all three, like 2, 3, 4, which are the childrens of 1 into the queue, right? That is this for loop. We are looping all the children of the element what we are processing, and we are putting those elements into the queue. Got it?
Yeah, got it.
Yeah, so let me know, like anybody, like stop me if you guys are having any questions. So I want to make sure you guys are everybody understand this algorithm. Very simple, but we need to put a little bit attention why we need two loops. Here is one loop and while loop, and here is for loop. Why we need two loops? That's a really important thing we need to remember. So processing includes three things: removing the element from the queue, printing that element value, and adding all of its children into the queue. So this is there is a three-step process. So I can put for easy remembering, like I can also do one thing. So remove DQ.
So, what happens when there is no child node in the
That's a
current
good
node?
question. Yeah, if there is no child nodes, it won't even execute, right? The for loop will not execute because if the child nodes is null, like child is, it won't even execute.
Okay. So it will
So
DQ,
for
DQ, and
each
DQ.
node, exactly. So only thing is number one, like remove the element from queue, and then step number 2 is print the element value. We are printing, and the number 3 is basically will not execute if we don't have any children. So for each, so here add all failed nodes of this current node to the queue. This is what we are doing here. So that's a good question. So if we don't have the basically if you look at here, this is empty, right? Whenever, like if there is no children, let's say for the node 5 or for the node 12, this is empty list. We created with an empty list. Childrens are empty. We never called children, adding the children, right? We did not add any children for 11, for 12. If you look at here, so we added only children for 8 and 6, 4, all these. So we did not add any children for 11 or 12. So what happens is this for loop will not execute. There is no children. It's an empty list. If you get an empty list, it will automatically take care. The C# engine will take care. It won't execute any of these statements. So is it clear to everybody? This is just the traversal. Okay, so we can execute the traversal. I can run the program, and also, like before that, I can show you the other one. Let me run it, so for easy understanding. So let's see what happens, and if what it prints the breadth first search or breadth first traversal. This is BFS, and here is the thing. So now if you want to compare this with the tree here, I can show you here. See this one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and see that 12, 11, 10. It printed in a right order, right? Always from left to right and level by level. This is the breadth first traversal. Now let's look at the answer here. So 8 found in the given tree and 15 does not exist in the given tree. See this? So these two are printing from the other method here. Run BFS. So what are we doing here? So run BFS will take two things: the root and the value to find, right? So value to find equal to value found, basically I'm just giving a boolean variable, value found equal to breadth first search of root and value to form. So if the value found true, that means we found the value in the given tree. If this is false, if this is giving a false, that means you did not find any value. Let's say if I'm saying 15, this value will be false, and I will say that this 15 does not exist in the given tree. Okay, so this is just a running program. Now what this breadth first search is doing? So it needs to return a boolean, and it will take the root and also value which we want to find. Let's look at this. It's almost exact the same, almost same as traversal. It's just a little bit ending condition will change. If you look at here, exact same lines. If root equal to null, false. In the previous program, we just said return because it's the void. The return data type is void here, which is like, I don't know what in other languages. We are not returning any data type. But in case of breadth first search, if you are giving an empty tree, what I can say, if you are giving a null for the tree, and if you want me to find 100 here or 15 or 8, I will simply say it does not exist because you given a empty tree. So that's why, because we need to return a boolean, we will return false if the root is null. Otherwise, that means there are some elements in the queue. Let's put that element in the queue, and let's take the same node here, node variable, and it's exact same statements until q is not null. Take the element, and here before, like we don't want to print the value, right? We are it's not traversal. So instead of printing, we will see whether the value you are looking is the value of the node. So node dot data equal to value to find. If you are looking for 1, we found 1 because the first element data is 1. So node dot data equal to value dot value to find. That means the current node value is equal to the value you are looking. Return true. Otherwise, this is not the value you are looking. There could be a lot of children, so we are simply adding all the children into the queue, and then we are ending the loop. So next time what happens? The one of the children will be dequeued, and value will be compared with the value to find. It's a simple. Instead of print statement, we put this statement. Is it clear?
Yes, sir. Can you explain the complexity of this program, time complexity? Like it
Sure.
will be
Yeah,
any
we will do that. That's a good
Yeah.
question. There is one more thing I missed here. Let's look at the 121, line number 121, which is not there in the traversal. In the traversal, after while loop, nothing here. In the traversal, if I go up here, so once the while loop completed, that means what that means? You traversed all the elements of the tree, right? Once the queue becomes empty, once the count of the queue equal to 0, that means there are no more elements to process. Same thing here. If the control comes here, that means we traversed the entire tree, but we did not find the value to find. Whatever the value you are saying, in case of 15, what happens? You traverse the entire tree, you never find 15 because there is no 15 in the given tree. Then it comes here. At that point, you need to return the boolean, right? What are you going to return, true or false? False, because you did not find the element, right? So here is another ending condition here. So there are two ending conditions, as I said before. One is if you find the element, that is one ending condition. You no need to traverse any of the children. Let's say the same example, Shivang said, do we have 8? Yes, 8 is there, right there. You no need to process 12, 11, 10 or any other children. That's it, just return true. That's one condition. Otherwise, the second condition is you completed processing of all the elements. You did not find the element, right? If you found the element, you should have written by the time. But if the control comes here, means you completed the processing of all the elements. We did not find the element what you are looking, so simply return false. Okay, that's why we have outputs here. So 8. 8 found in the given tree and 15 does not exist in the given tree. Is it clear, or any questions before we discussing the complexities of this algorithm? I want to make sure. Cecilia, Modit, Karanya.
It's clear,
It's
sir.
good. Yeah.
Yeah, go ahead.
I'm sorry. I'm sorry.
Yeah, it's good for
No
me.
problem.
I just need to review it later again.
Sure. Yeah, I will send you the link to this algorithm. So it's a basic. Just basically we are doing exact same thing what we are doing on the traversal. So only thing is lines will change. We are looking for the value instead of printing. Yeah, go ahead, Shivang. You have a question?
No, sir. I was just saying it's clear for me.
Okay, good. Modit, are you clear on this?
Yeah, like I also need to like see the whole code, like revisit all this.
Definitely, yeah. So I will send this. You revisit. Yeah, so it's a basically, very quite simple few lines, but we need to understand how we need to, you know, writing this. Basically, if you understand the basic sequence, if you can close your eyes and see, okay, what are we doing? We are just adding root to the queue and then loop. In the while loop, we are taking the first element from the queue and processing. Processing involves 3 steps. So there are 3 steps in the traversal here: removing, printing, adding children. Here also 3 steps. So basically the same steps will execute. So I can copy this here. So the first step is basically remove the element from the queue. And second step here, rather than printing, here it says print the value. But here, second step is check if the value of the current node is you are looking. Right? That's the second step. When you visited a node, check whether that is 7. When you visited a node, next node, check whether that is 7. Right? So, or maybe 8. If you're looking for 8, so that's what you are doing. Visually, that's what you are doing. Is starting at first level, 1 is not 7, 2 is not 7, 3 is not 7, 4 is not 7, 5, 6, 7. Here is 7. Just think about what our eyes is doing. That's what we are coding. Right?
Yeah,
So
yeah,
that's the
yeah.
first step. Like, yeah. So second step check if the value of the current node is what you are looking. What is the third step? No, this is not the value what we are looking. That means step number 3. Same thing here. Whatever the step number, or add all the child nodes of this current node to the queue, because they will be processed in the next iteration. We don't want to check the value of the nodes at this point, because we have to go in a breadth first search manner. So what I'm saying is, you don't look your eyes like this. This is not a breadth first search. If I ask you to look for 7, look for 1, look for 2, 3, 4, and then look 5, 6, 7. That's a breadth first search. So next we are discussing about depth first. Then you look like this: 1, 2, 5. We did not find 7. 1 already visited. 3, 6, 12. We did not find 7. 1, 3, 7. Yeah, we found 7. So that kind of searching is called breadth first search. You go down, and then you go down here, and then you go down this side. So then you find it. So that's what we are going to discuss next time. So basically after this program. So these are the 3 steps in the breadth first search. Now let's discuss about the complexities. Can anyone tell the complexity? Control plus minus, zoom out. Control plus minus what? Control plus minus or minus? Maybe minus. Yeah. Okay. So now I just zoomed out a little bit. So here is a simple algorithm. We have 4 like, of course this is a main program. Other than main, we have 3 more methods here. First is traversal, Second is the breadth first search, and this one is which runs the breadth first search. Are we good here? Shall we go to the next one? Or maybe complexity. Let's discuss about the complexity. So what is the complexity of breadth first search? Any guess? Karanya, yeah.
O of n.
Exactly. That's correct. Often. Why it is often? Complexity is always worst case, right? Why it is O of n? So we have how many elements here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 elements in this tree. So it's order of 12. So why it is O of n?
We are traversing each element only once, and we are traversing the
Yes.
whole tree.
Yeah, in the worst case, you have to traverse the whole tree. So let's say example, ask you to find 15. What are you going to do? Unless you traverse every element, you don't know whether 15 is there or not, right? So the max thing is you have to traverse all the elements and say there is no 15 here. So all the elements means, let's say if you have n elements, so you traverse n times. So that which is order of n. So is it clear? So Shivank?
Yes, sir. Makes sense.
So basically that's what it is. So order of n means worst case. Basically every time like the best case and worst case. Always like the complexity is, we will say in the worst case scenario, you have to traverse all the elements. In the best case is order of one. What is the best case order of one means? Let's say if I ask you to find, do we have one or not in the tree? What is the complexity of that algorithm?
Like the first
Just
node. Yeah.
order of one, because you can simply say just like you just visit the node, root node, and say you found one. It won't even execute the while loop second time. It will enter into the while loop. Of course, it will enter into this here. Let's say here, right? So you added one here into the queue, and you removed the one here, and you found the one here. Just it will execute. It will not visit any of the child nodes or anything. The best case is order of one, but complexity always worst case. So that's the difference. If you go because the main problem here is it's not a binary search tree. If it is binary search tree, you can decide whether you can go left or right. I will discuss that in detail in the next class here. So we have binary search tree. What is binary search tree? And finding an element in the binary search tree, and the complexity of that binary search tree, and also inserting a new elements, deleting a new elements. These are all very complex in algorithms, very interesting, and I will discuss. But this is different. Binary search tree will give you a better option because they are in a particular order, and you can decide whether you can go left or right. So you no need to traversal every element of the tree. You can find number 8 in a much faster way if it is a binary search tree. If it is a normal tree, there is no order. 8 could be anywhere. It could be here, 8 could be here, 8 could be here, 8 could be here, any place. So you cannot decide where you know which way you want to go. So you cannot avoid any of that element. You have to visit every element. So that's the order of the binary search complexity of binary search tree. We can just search. So if you want, I'm sure it is order of n for sure. So but I can verify. I can double check. So we can double check here. Complexity BFS. Oh, it says a different way. The complexity of BF is O of V plus E. So it's almost like order of n, but they are expressing in a different way. So where adjacency list used, what is the complexity? V is vertices and E is edges. The complexity of DFS is O of V plus. V is same thing actually. So the complexity of DFS and BFS is same. So V is basically the vertices, E is edges. So they are representing in terms of vertices and edges. So vertices means the nodes 1, 2, 3, 4. Those are the vertices, and edges means this is called edge. So this is one edge, this is one edge, and the that's called an edge actually. So they are representing in a different but it almost like complexity of number of number of nodes. So in both DFS and BFS, every node is visited but only once. The big O times is order of n for every node in the tree. See, this is exactly what we just discussed. For BFS, which traversal all the nodes at given depth in the tree, and USA queue implementation with the width of the tree matters. The space complexity of BFS is order of W, where W is the maximum width of the tree. So space complexity, yeah, this is another thing. We did not discuss about space complexity. So what is the space? How much space do you need for BFS? What is the maximum space? So they tell in the given example here, oh, I already messed up the tree a lot. So at max time, at the max, how many, number of elements we need to store at the max?
All
Which
the
is
elements,
equal
sir.
to, no, not all the elements. See that you never store all the elements at once. See, you removed one, then only you added
Oh,
2, 3, 4. Right?
uh,
Look at
three actually, sir.
the look at the statement here. You remove the
Yeah,
element
yeah.
and then only you're adding the elements, right? So you remove the one and add the 2, 3, 4. So once you add the 2, 3, 4, the size is 3 here, right? Once you remove 2, you add the 5 here. That is also 3. Point. So what is the max time is, let's say when you're processing 4, by the time you're processing 4, you already have 5, 6, 7, 8, and you're adding 9. So I think the third level has max number of elements, right? We have 5, 6, 7, 8, 9, which is like 1, 2, 3, 4, 5 elements. So when you're processing 4, you need to have the size of 5 elements. That's the max size. That's what they are saying here. So the space complexity of BFS is order of W, where W is the maximum width of the tree. What is the maximum width? If you look at the width of the level 1 is 1. Width means basically the number of elements at each level. So what is the number of elements at the level 1? Just 1. What is the number of elements at the level 2? 3.
3.
Are you guys following? What is the
Yeah.
number of elements at the level 3? 5, right? 1, 2, 3, 4, 5 elements. And how many number of elements at the level 4? Just 3. So they're saying at max the queue will have this much width. We need at least the queue size of 5. That's what they're saying. Because at the time of processing 4, you process it to 1, 2, 3. And when you are processing 4, you already process it 2. That means we have 5 here, and we have 6 also here, 7 here, 8 here. When you're processing 4, you need to add 9. So you added 9. So now look at how many elements. 1, 2, 3, 4, 5. This is the max time. This is the max space you need at any point in the execution of this tree. That's what they're saying, the max space complexity. Of course, we don't allocate memory. We don't, when you are creating a queue, you don't say, hey, take the queue of 10 elements, take the queue of 100. We don't do that. But we are estimating how much size you need, how much memory you are wasting. Are you taking 5 GB? Are you taking 10 GB? No, we are just taking whatever the max number of elements at a tree. If you are given a tree with a million elements in this level, it may take to 1 GB, 2 GB. We don't know. It may take up the whole RAM. You screw up the entire memory of that system. It depends on the given input. So when the interviewer asked about, hey, what is the space complexity, you need to say that, hey, this is the max depth of the tree or the maximum width of the tree. That's what the exact notation here. Is it clear to everybody or is it confusing?
It's clear, sir.
what I do is
It's clear.
good thing. I will put it here. So I will put it in the notes as well. So which is good. Okay, this is the complexity. I think we are almost like 8:50 now. So we always have, we cannot process everything at once, but I want to go slowly only because if you guys are understanding, that is important rather than completing it. Of course, we did not complete DFS. If you want me to complete in next 10 minutes, like, or if we can discuss it at least.
Uh,
So,
Actually, sir, I
yeah,
have
go
to
ahead.
go. Sir, I have internals coming up next week. So
Sure. That's no problem.
yeah,
But you like
and
the session?
yeah, it's very good, sir. It's very informative and it's very
Yeah.
productive, sir. And I just want to say one thing. Uh, in 1 week, how many times we are doing this? Like,
Actually, I have full busy schedule with the work and family and everything. I'm just meeting once a week, so
so where are you
exactly the
from?
same time. I am from Seattle, USA. I
Nice.
natively from Andhra. I'm a Telugu. Yeah. My main
Yeah,
intention is help the Indian community there in India. So because it's like early
it's
morning 7 o'clock for me.
it's very
So I
nice
will
of you,
wake up
sir.
early and thank
To
you.
do
Yeah,
such thing. Yeah, thank you for so much for. And I just want to say to everyone, like, I'm doing lead code every day. If someone wants to join me, like for questions and all for discussions, so feel free to ping me on Discord. I'm there in the group.
that's great. That's great. Are you part
Yeah,
of this group? Let me see. Is it in this group? Oh yeah, Shivang, right? Yeah, I can see now.
yeah,
Yeah,
yeah. So
awesome,
feel free to ping me, guys, if you wanna join. Yeah. Uh, it's
awesome.
very nice of you, sir, to do such things.
No problem. You can
Very
just
less
call me
number of people.
Suresh. I don't want to call me Sar or anything. I'm just, of course, I'm old, but just call
No,
me
it's fine,
Suresh.
sir. It's just respect I like to give. Yeah,
No
it's
problem.
fine, sir. Yeah, thank you, sir.
Uh,
Uh,
awesome.
we'll meet again, sir. I have to go.
Sure. Yeah, we can meet again. If you want, we can. You can also look at the recording. We will discuss maybe
Yeah,
another 10
I'll
minutes.
sure look at the video. Basically, I have a doubt in trade. That's why I joined today. So for me,
Sure. Yeah.
stacks, linked list, and queues I've done. Uh,
Uh-huh.
Trees and graph I have uh, like I've not. It's very weak for me, so I have to prepare for
Very
that.
good. Yeah, this you joined at the right time because I'm explaining
Yeah,
every concept of the tree
actually,
and graph.
yeah. Thank you, sir. It's fine.
Awesome. Yeah. Cool. What about Karunya and Cecilia? Do you want me to discuss the DFS or shall we discuss next week?
We shall discuss next week, Suresh. That's too loud here.
Awesome. Yeah.
Same.
Good. That's good. So awesome. So Mudit, are you okay? So shall we meet next week same time?
And so also, if you are doing this like trees, can you do some questions on trees also, like from lead code or something, if it's
Yeah.
possible for
Yeah.
you?
Definitely. That's the thing, right? If you look at here, these questions are from this one, the coding. What is that? The CI, CA, like
Cracking the coding interview.
yeah,
Okay,
cracking the coding interview. Yeah, CC,
okay.
CICC, whatever.
I have that book, sir. It's very nice, sir.
Yeah,
But
this
I
is
haven't reached the
yeah, this
trees
is
part
like
yet.
page number 224, cracking the coding interview, and even the find in order successor is also one of the question in that book. Even this one is also page tree balance,
Yeah.
minimal
Okay.
tree.
Nice, sir.
I'm covering most of the questions from it. Yeah, from that book.
Yes, sir.
Cool,
So
awesome.
yeah,
Then we will meet again next week. Then, okay.
yeah. Thank you, sir.
Thank you,
Thank
Awesome.
Suresh.
you.
Yeah. Yeah. Have a
Bye.
nice week, everybody. Bye.
Bye.
Bye. Bye all.
Bye, everybody. Bye.